Ladies and gentlemen, today's lecture is going to focus on general metallurgy. The general metallurgy is the process of extraction of metals from the ores and refining them. Before I go into general metallurgy, I want to give you how steel is being made. I will give you the synopsis of all stages of steel. To actually in this present time, to start from the scratch and make steel, there are different ways of producing steel. We have what we call the blast furnace. I will treat each one differently in other lessons. So I'm just going to give you the brief synopsis of all of the steel making. We have blast furnace. Then we have open heart steel making. We have oxygen converter, and we have electric arc steel making, and then we have foundry steel making, and then we have the rolling mills. So at other lectures, I am going to give you the breakdown of each of these, how we make steel in different ways, and which one among them are more economical than the others. You will see as we go on with the lecture how steels are being produced. Today, our focus is going to generally make you to understand what is general metallurgy, what is metallurgy generally, what it's all about. So, in the word, we're looking at the word metallurgy, it's to tell you, by putting metallurgy, there's a metal there. Then the logy, what does that mean? So it's the process of making it. That's why we call it metallurgy. Now let's discuss about metals. Metals are one of the two major classifications of elements. Non-metals being the other. Almost all metals are found in combined state as compounds on the crust of the earth. This due to their high reactivity. However, there are few exceptions, such as gold, silver, copper, platinum, bismuth, which are found in the free state due to their low reactivity. Aluminium is the most abundant metal in the Earth's crust, followed by the iron calcium. So I am going to give you the different kind of ores, metals we have, metals and the percentage we have. Aluminium consists of about 7% weight. Then we have iron, which is Fe, the formula. Aluminium is Al, which is about 4% weight. Then calcium has about 3%. Sodium has about 2.5%. Potassium has about 2.5% as well. Magnesium has about 2.0%. Then titanium has about 0.6%. So metallurgy, the various processes involved in the extraction of metals from their ores and refining them are known as metallurgy. So if somebody asks you what is metallurgy, by all means, you are supposed to be able to tell them as to a layman that is the various process involved in the extraction of metals from their ores. So you hear about me talking about iron ore. So what is iron ore? A great example of iron ore is what we have in Itape, which is in Kogi Central in Nigeria. That iron ore is the extraction, because it consists of compound, is the extraction of metal from the ore itself. So that's what we call metallurgy. So there are various ways of doing that, and we will discuss about how those things are being extracted. So this is what we call metallurgy. And then when you extract them, you refine them, then the process of extracting it and refining it is what we call metallurgy. Because if you just extract the ore and you don't refine it, then just like in oil, in the crude oil. So if you extract the good crude oil and you don't create a refinery to refine it, then you are not actually getting the oil you need. So it's typical, the same process. Now, minerals. The natural materials in which the metals or their compounds occur in the earth are called minerals. Let me repeat that again. Minerals are defined as the natural materials in which the metals or their compound occur is what we call minerals. Now, let's look at the ore. Let's look at the ore. Those minerals from which the metals can be extracted profitably are called ores. Any minerals at which the metals can be extracted from are called ores. So if I cannot extract a metal from minerals, then they are not ores. So in another layman's definition. So gangue or matrix, the rocky impurity including silica and earthy particles present in an ore are called the gangue or matrix. So because when you are extracting ore from the soil, it contains particles, sand, it contains different particles. So that's what we call gangue, or we call it matrix. So we call it the rocky impurities, including silica and earthy particles present in an ore are called the gangue or matrix. So I want you to get that clear so that those of you who are studying metallurgy, you know the meat and core of what metallurgy is all about. You need to know exactly. That's why you can't have an ore without the proper refinery. So basically, when you take example of Ajakuta and Itape, you get the ore from Itape, but you refine it in Ajakuta. So that is, they go hand in hand. So you can't have iron ore without refinery. It's just like the same way you cannot have production of oil without refinery. You get a crude oil and you don't refine it, it's not oil. So the metallurgy goes hand in hand with the same process that is being adopted in refining oil and getting the petrol and all those kind of things, petroleum and all those things. Is the same process we go through when you're dealing with metallurgy. Now it's a little bit difficult because actually with the oil it's in a liquid form. So but the iron also is in a liquid form, but it's more of a solid liquid. It's more of a thick liquid than what the oil we get and then refine. So we will talk about all of that. Now, ores occur in the form of compounds. That's all. It's compound. When you talk about compound, you should understand, what compound means. In the layman's language, a compound is two elements or two elements coming together to bond together forms compound. In science, if I have oxygen reacting with carbon, I'll form carbon dioxide. So getting the carbon dioxide becomes a compound because I have two atoms reacting together to form that carbon dioxide. So, and that's in its simplest form. So I want you to get that very clearly. So let's look at the classification of ores and type of ores. The type of ores we have oxide ores. Oxide ores in the metallic stage, what we get from the oxide ore, we get aluminum, copper, and iron. So when you hear oxide ore, so you are dealing, the end product you're going to get as metal, you're going to get aluminum, you're going to get copper, and you're going to get iron. So the moment you get an oxide ores, those are the three properties you're going to get, the three things you're going to get from as a metal from the ore itself. You're going to get aluminum, you're going to get copper, and you have iron. Now let's look at the compound of each of these elements of this element of the element I've just called, which is the oxide. Under the aluminium, to get aluminium, we have the compound that contains aluminium is called bauxite. Here, bauxite, which is the aluminium dioxide, aluminium oxide, reacts with water to form bauxite. For copper, you have copper. In order for you to get copper, to get the compound, it reacts with gas, with oxygen, in order to form cuprite, which is from that compound you heat it, you get copper. Then we have iron. Under iron, the compound that consists of iron is called the hematite. It has iron and oxygen combined as a compound. So in the process of heating it, you get iron. So you have magnetite as well. So for magnetite, you also heat it to get iron, because magnesium is an ion too. So you get an ion. So then you heat it because it has oxygen reacting with it to form that compound. Then you have what we call sulfide. Under sulfide ores, which is the type of ore now, we have sulfide ore. The first one I made mention of, I said we have oxide ore, we have sulfide ores, and we have carbonate ores, and we have halide ores. Those are the 4 categories of ores we have. I want you to get it again. Oxide ores, 1. Sulfide ores, 2. Carbonate ores, 3. Halide ores, 4. Those are the 4 major ores we have in ETAP A as we speak right now. 4 ores. Can anybody repeat it for me again? I want you to try your knowledge in basic metallurgy. So the first one I say is what? Oxide ore. Second one I said is what? Sulfide ore. Third one I say is what? Carbonate ore. Fourth one I said is what? Halide ores. So remember that as we go in the lecture process. This is lecture 2 anyway. Lecture 1 has already taken place. So in this lecture, let's look at the sulfide. I have treated the oxide ores already, and I told you the metals and the compound that consists of the oxide ore. Let's look at the sulfide ores. Under sulfide ores, we have 3 things that are important that we get out of this. We get iron again, so we get copper again, and we get zinc. Remember, on the oxide ore, we get what? We get aluminium, copper, and iron. On sulfide ores, we get iron, copper, and zinc. It's very interesting, right? Okay. So on iron, we get, on sulfide ores, the compound that is formed in this is called the iron pyrites, which is FES, iron pyrites. It's FES. So this is the compound that is formed that we extract iron from. For the copper, we have copper glands, which is copper reacting with sulfur to form a compound to get a compound glands. So, and we extract copper from compound glands because it's a compound. Now, also we extract another one, copper pyrites. The copper pyrites has copper, iron, and sulfur together, which makes it a compound. So this thing has to be broken by source of heating it to get your copper. Now let's look at, for the zinc, we have what we call zinc blende. Here, the compound that is formed is zinc and sulfur coming together to form a compound. So let's look at the third one, which is carbonate ores. The carbonate ores consist of calcium. zinc. These two things, it consists only carbonate ores. So when anybody is telling you about carbonate ores for the ores, the first thing that comes to your mind should be, oh, it consists of calcium and zinc. That's it. Then what are the compounds that form that we extract the carbonate ore from? We have limestone, which is called calcium carbonate. Limestone is called calcium carbonate. In the recent, a calcium carbonate is what? Salt. Now, we have calamite. Under calamite, the compound that consists of calamite is zinc and carbonate. So this one has to go through the process of heating in order to extract your calcium as well. So let's look at halide ores. Halide ore, you have the sodium. Under halide ores, the metal that we get out of the halide ores, we get sodium, we get calcium, we get silver, we get aluminum. So in these halide ores, you have rock salt, right? The rock salt, the rock salt consists of what we call the compound that it entails is sodium and chloride. Then we have calcium. So the calcium, this is called fluorspar. It consists of calcium and ferrous. That is called fluorspar. Those form that compound. Then we have the aluminum, which is, we call it chloride. So chloride is formed by having a compound of sodium, aluminum, and fluor. So these three elements forms the compound. Now, looking at all of this, let's look at the process involved in metallurgy. The process involved in metallurgy, so we'll talk about the main process and we'll talk about sub-process. So the main process, one, I'm going to list about 4 of that. We have concentration of the ore, which is the removal of unwanted metals and gag to purify the ore. 1. 2, we have conversion into metal oxide. 3, we have reduction of metal oxide to metal. 4, we have refining of impure metal into pure metals. So let's look at the first one that I've just mentioned. I talk about concentration of the ore, so which is the removal of the unwanted metals, and gag. I have told you what gag means, to purify the ore. Now, the sub-process to do the main process is hydraulic washing. You can go through the process of hydraulic washing to do that. You can go through the gravity separation, C, Ford flotation, magnetic separation, the chemical separation. All of those things falls on the sub-process of a concentration of the ore. That which is the removal of unwanted metals and gag to purify the ore in order for you to get the purity ore, which is the iron. Now, conversion into metal oxide, which is number 2 now. The calcination of the carbonate ore, 1, under the sub-process. We can go through in order to get conversion into metal and get oxide, we have to, first we have to use the calcination. The sub-process now, we use the calcination for carbonate ore. The next one is roasting the oxide, or the conventional method, which is the oxide, is roasting it for sulfide ore. So you roast it and you get the sulfide. Sulfide is a gas, So when you hear sulfide, and I want to tell you, if you're doing metallurgy or you are doing any kind of science or any kind of chemistry or something like that, if there's a leakage of sulfide, hydrogen sulfide, which is hydrogen sulfide, The other is rotten egg. The moment you are in the lab, you perceive rotten egg cell, you know it's hydrogen sulfide, which consists of hydrogen. It's a compound again. It consists of hydrogen and sulfur. So it forms hydrogen sulfide. And when you perceive the odor, it's like a rotten egg smell. So this is basically a secondary school chemistry. You learn that in secondary school, when you are given lab to perform, and the first thing you just say, you start, you mix the chemicals, you take a hydrogen and you mix it with sulfur and you get hydrogen sulfide, and the next thing you start perceiving the odor of a rotten egg. So I remember when I was a kid in high school, that's how we determine in chemistry lab. So everybody knows that. If you're a science student, you definitely have to know that. Now, so that is that. So I will go into the main process of reduction of metal oxide to metal. We talk about concentration of the ore. We talk about conversion into metal, and we take all the sub-process for it. Now, my third one is reduction of metal oxide to metal. In order for us to reduce the metal oxide, then in order to get metal, we go through three methods or three sub-process, not three sub-process. First, roasting mercury is produced by roasting cinnabar, which is HGS, in air. B, the number two, reduction using high reactive elements. Example, aluminum reduces manganese dioxide to manganese. Now the third one is electrolytic reduction. Highly reactive elements such as sodium and mercury are obtained by electrolytic reduction when the metal is deposited at cathode. You have anode and a cathode, so make sure, or metal usually, will be depositing on the cathode side. So I want you to get that. The anode is the positive, the cathode is negative. Well, so most of the metal are we magnet to the cathode, which is the negative side, because the metals are positive. So it goes onto the negative side. So when you're dealing with chemistry, you will be able to know that very well. Refining of impure metal into pure metals. How do we do that? The sort process A. Electrolytic refining of copper, gold, tin, lead, chromium, nickel, etc. We have so many of them. B. Liquidation process. It was a sub-process for tin, lead, and bismuth. C. Distillation process for zinc and mercury. D. The oxidation process for iron. So I gave you 4 categories now on refining of impurity metals into pure metals. In order for me to refine my impurity metals to pure metals, I have to go through 4 sub-process. I can use the electrolytic refining of copper, gold, and tin, lead to get my metal, to get my copper, to get my gold, to get my tin, and to get my lead or chromium. So, and the next one, or nickel. These are all metals. Then the second one I talk about is liquidation process. Here, for you go through the liquidation process, you get your tin, lead, and bismuth. So then the final one I say, the oxidation process from iron. You oxidize the ore, and then you get your iron. Those are the things that you need to know. Each of these main processes mentioned above are discussed in details. So let's look at the concentration of the ore, first of all. 1. Talking about the concentration of the ore, I would mention three categories for. I'll mention 3 categories for the basically concentration of the ore. Number 1, I'll talk about hydraulic washing process. Then I'll talk about froth flotation process. Then I'll talk about magnetic separation process. Then I'll talk about chemical separation process before I go into the next one. Now, under the hydraulic washing process, which is also known as gravity separation, this process separates the heavier ore particles from the lighter gag particles. This is done by washing them in a stream or jet. This process separates the heavier ore particles from the this process separates the heavier ore particles from the lighter gauge particles. This is done by washing them in a stream, or if you call it stream or you call it jet, of water over a vibrating slope. You kind of make it in form of a slope, a positive slope. Have a positive slope. This is what we call positive. Negative slope will be like this. Here is a positive slope. You know, you can either through negative poles or positive slope, but usually I prefer the positive slope. So you kind of have your this thing, your lining, or at which this thing is gonna come down in a slope form. So you have this slope table with grooves. Denser ore particles settles in grooves. Lighter gag particles are washed away. So because they are lighter and thinner, they are washed away, and the heavier one settles at the gag because we create in form of gag. So that kind of collected. Now, that's the hydraulic washing of gravity separation. That's how you separate it from, because when you get the ore, what happened? It is mixed with particles. So in order for you to separate it, that's how you do it. Then we have the froth flotation process, which I will address here. In this process, separation of the ore and gag particles is done by preferring wetting. This process is generally used for sulfide ores of copper and zinc. The finely powdered ore is mixed with water and a suitable large tank. A current of compressed air agitates the mixture. The ore particles are wetted by oil and forms a froth on top, which is removed. The gag particles wetted by water settles down, or preferentially wetted by oil is removed as froth. Gag wetted by water is removed after it settles down. So when it is, because it's so minute, until the water settles down before you can have that removed. You know, it settles in the bottom. That's the way, because the gag is very fine particles. So you let it settle down, then that's how you remove it. Then we go into, I have just discussed about froth flotation process. So let's look at the magnetic separation process. The magnetic separation process, this process is used in the extraction of metals which exhibit magnetic properties. For example, in the extraction of iron crushed magnetite ore, which is iron particles, are separated using their magnetic property. The pulverized ore is moved on a conveyor belt. Electromagnetic wheel of the conveyor attracts only the magnetic particles into a separate heap. So any particles, so we have the belt, and in the belt as it's moving, it only attracts the metal, because you know there's a light on light poles in science. You know the negative and positive poles attracts each other. Negative and positive attracts. So that's basically what is happening here. So it only attracts the iron and the magnesium in this case. Now, and the rest flows away. Non-magnetic properties will flow away. Now, Only the magnetic particles are attracted by the magnetic wheel. These particles fall separately into different heaps as shown in the diagram. I can create a diagram. I don't have the diagram to show you right now. So that means the magnetic particles is being distracted, and we have a collector. We at the point of time where we have the collection. So the other one are being discarded, and the magnetic particles now are being conveyed to another a collection section. Now, let's look at the fourth one, which is chemical separation. So in this chemical separation, there's a reaction going on here. This process utilizes the difference in some chemical properties of the metal and gag particles of their separation. For example, the Bayer's process of aluminum extraction. The bauxite ore is treated with hot sodium hydroxide solution. Water-soluble sodium aluminate formed is filtered to separate the undissolved gag particles. Again, undissolved gag particles is the residual particles. So sodium aluminate is further processed to get aluminum oxide. That's how you do it under chemical separation. Now, let's look at the conversion of concentrated ore into metal oxide. So what is conversion of concentrated ore into metal oxide? It is easier to obtain metals from their oxide rather than from carbonates to sulfides. So the ore is first converted into oxide. A carbonate ore is first converted into oxide ore by calcination. A sulfide ore is converted into oxide ore by roasting. So you have two processes here. The first process, under the conversion of concentrated ore into metal, you have to go through two processes in order for you to be able to convert it. Now, they tell you it is easier to obtain metals from their oxide rather than from the carbonate sulfide. So the ore is first converted into an oxide. So the ore will be converted into an oxide. A carbonate ore is first converted into oxide ore. So you have from carbonate oxide, you convert it to oxide ore. Then before you convert it again into sulfide. So that is the process you do. Now let's look at the calcination before we talk about roasting. The calcination process, it is the process of the heating the concentrated ore at the temperature not sufficient to melt the ore. The water content and the volatile impurities also get expelled. Zinc carbonate in its ore calaminate, which is zinc calaminate, is calcinated to obtain zinc oxide. So now in an oxide form, you can do the calcination process. So you do the calcination of zinc carbonate, you get zinc oxide and carbon dioxide. Carbon dioxide is a gas. Simple as that. On the process of roasting, it is the roasting process now. Under the roasting process, it is the process of heating the concentrated ore in the presence of excess air. Volatile impurities also get expelled. Zinc sulfide in its ore zinc blend. Zinc sulfide is ZNS, so we call it zinc sulfide, is roasted to obtain zinc oxide. So you have the zinc oxide, you roast it. When you roast it, it reacts, the reaction takes place, and then you form zinc oxide. So the sulfur is separated. So you roast it, you get zinc sulfide, you separate the zinc from the sulfur. So you get, this has to react with oxygen, so by roasting. So you roast it through a process of heating. You get your zinc oxide. So you now get your zinc chloride, then you get sulfur dioxide, which is the also gas. The mercury oxide is obtained by roasting cinnabar with sulfur in air. So under this case, you have the zinc reacting with the oxygen, and then we are going to have your zinc oxide and sulfur dioxide. Now, let's look at the calcination and roasting. One, under calcination, you convert carbonate ores into oxide. Two, ore is heated in the absence of air. So there will be, when you heat it without air inside, that's calcination. For roasting, you convert sulfide ores into oxide. Now, next, the second part, ore is heated in the presence of air. Now, the difference here, under calcination, when ore is gotten, ore is not heated. Oil is heated in the absence of air. In this case, there's no air, so you have to kind of heat it in a vacuum. So create a vacuum. A vacuum means there's no air in it. That's the only process you heat it. Then you extract your iron. Under the roasting process, ore is heated in the presence of air. Air is part of it, and that is how you do it. Calcination and roasting process are self-process. This process cannot be used for oxide and chloride. You cannot use this process for oxide. This process cannot be used for oxide and chloride process. Why? So that's an interesting thing that you need to know. Reduction of metallic oxide or metal. The reduction, this is the conversion of metal oxide into metal by removal of oxygen. Simple. It's called reduction. Generally, the three methods used are reduction by heating the oxide, chemical reduction, and electrolytic reduction. So electrolytic reduction 1, chemical reduction 2, 3 is reduction by heating of oxide. Now, let's look at reduction by heating alone, which we call the heating process. The oxides of metals that are low in the reactivity series can be reduced to obtain the metals by heating their ore. For example, mercury oxide, which is HgO, obtained from its ore mercury sulfide, when heated to about 200 degrees centigrade, forms a mercury metal. Simple. So you have mercury sulfide, react with air, you roast it, you get your mercury oxide and sulfur dioxide. Simple. Next phase, you take your mercury oxide now, two process. You heat it again with the reduction process, you get mercury and oxygen. So oxygen is gas. Now, metallurgy is a very interesting subject, and the moment you get hang of it, you love it. It's just how it is. There's no two ways about it. So I found it very interesting. When I was a student, I literally enjoy, studying metallurgy because, you can really see what is happening. A chemical reduction process. Under this process, the oxide of metals that are in the middle of the reactivity series are reduced to free metals using chemical reducing agents such as carbon, aluminum, sodium, and calcium. 1. Reduction by carbon process. Oxide of metals like zinc, iron, copper, nickels, tin, and lead are reduced using carbon as the reducing agent. Carbon can be used only if it has greater affinity of oxygen than the metal. For example, carbon can reduce copper oxide to copper, but it cannot reduce calcium oxide. Why? It can reduce zinc oxide, but not calcium oxide. So we will look at that. Zinc oxide react with carbon. We're going to have zinc metal and then carbon monoxide, which is a dangerous gas. Carbon monoxide is a dangerous gas. We call it a laughing gas. Now, reduction with the aluminum by thermite process. Metals which are too active to be obtained by the reduction of their oxides with carbon are reduced using aluminum, which is more powerful reducing agent. Chromium and manganese oxides are reduced using aluminum. The reaction is highly exothermic. What is exothermic? We have endothermic reaction, we have exothermic reaction. Endothermic reaction is a reaction that is done cover up. We call it endo. Then the exothermic reaction is a reaction that is exposed. So know the difference between endothermic and exothermic reaction. Now, in this case, you get your chromium reacts with aluminum. You're going to form a chromium metal plus aluminum oxide. Then you take your magnesium, react it with aluminum. You're going to get your manganese metal. You extract your manganese metal, and then you get aluminum oxide. Now let's look at the electrolytic reduction process. Under the electrolytic reduction process, the oxides of the chlorides of highly reactive metals like sodium, magnesium, aluminum, calcium cannot be reduced by using carbon aluminum, which are still seeing. The electrolytic reduction is the process used to extract the above metals. Molten oxide or chlorides are electrolytes. The cathode acts as a powerful reducing agent by supplying electrons to reduce the metal ions into metal. Fused alumina, molten aluminum oxide, which is also known as molten aluminum oxide, is electrolyzed in a carbon-lined iron box. The box itself is the cathode. The aluminum ions are reduced by the cathode. So you get it now. So in this case, you have aluminum ion reacting with electrodes to form aluminum atom. Under magnesium, manganese chloride, you do go through the process of electrolysis of it, you get magnesium and chloride. Simple. Let's look at refining metals. This process ensures the separation of even the residual impurities from the extracted metals. Refining metals are different from different metals. The metals depends upon the purpose for which the metal is to be used. Refining can also be used to recover some valuable byproducts such as silver or gold. Now, the two main categories of refining are physical methods, which consists of liquidation, distillation, and zone refining, which is also known as fractional refining. Now, chemical methods are oxidative refining, electrolytic refining, and Van Akel method, which is known as vapor phase refining. Now, let's look at the liquidation method. Under the liquidation method, readily fused metals at low melting points, like tin, lead, bismuth, are purified by liquidation. The impurities do not fuse and are left behind. Now, Let's look at liquidation. That's liquidation method. In this process, the block of impure metal is kept on the sloping floor of the hearth and heated slowly. The pure metal liquefies and flows down the furnace. The non-volatile impurities are infusible and remain behind. Let's look at the distillation aspect of this. In this process, metals with low boiling point, such as zinc, calcium, and mercury, are vaporized in a vessel. So under the vapor, it means that it's heated up and then the vapor goes out. So it are vaporized in a vessel. The pure vapor are condensed into pure metal in a different vessel. The non-volatile impurities are not vaporized and so are left behind. Again, that's how you do the extraction. Oxidation method. In the process of oxidation, in this process, the impurities are oxidized instead of the metal itself. Air is passed through the molten metal. The impurities like phosphorus, sulfur, silicon, and manganese get oxidized and rise to the surface of the molten metal, which are then removed. So this, you see why I say metallurgy is fun? Aren't you enjoying the lecture? I'm sure you are. Now let's look at the electrolytic aspect of method, refining method of this. The electrolytic aspect of refining steel or refining ore. We are dealing with ore now before it goes into the making of steel and all those things. So in dealing with the electrolytic refining method of ore, the process of the electrolysis is used to obtain very highly purified metals. It is very widely used to obtain refined copper, zinc, tin, lead, chromium, nickel, silver, and gold metals. That's the same process they use in the extraction of gold in South Africa, which is, in this process, the impure slab of the metals is made at the anode. A pure thin sheet of metal is made at the cathode. Third one, a salt solution of the metal is used as the electrolyte. The salt usually serves as an electrolyte. Salt. You have to understand that in chemistry. Now, in this case, on passing current, pure metal from the electrolyte is deposited on the cathode. The impure metal dissolves from the anode and goes into the electrolyte. The impurities collect as the anode more below the anode. Methods of obtaining metals very highly purity. In this case, the requirement of very high purity metals has increased due to the advancement in space and atomic energy and semiconductive devices. For example, uranium, used in the nuclear plants. So you must be thinking this must be a nuclear physicist, but this is a fact. Should not have more than 1 part per million, which is 1 ppm of boron. Boron in excess of this limit, if it has more than 1 ppm, if boron, you have existence of boron for more than 1 ppm, which we call it 1 part per million. 1 part per million is the ppm. Boron in excess of this limit will stop the chain reaction initiated. By absorbing the neutrons released, it will absorb it. Now, germanium used in semiconductor devices should not have more than 1 part of copper in 10 million parts. zone refining, which we also call fractional crystallization. This process is used in refining of germanium. It is based on the property that when an impure molten metal is cooled, gradually, when it is cooled gradually, only the pure crystals of the metals are formed. The impurities that are left in the remaining part of the molten metal, a circular heater fitted around an impure germanium rod is slowly moved from one end to the other. The heater melts a band of a metal, and as the heater moves ahead, the pure metal crystallizes out of melt. As the heater moves ahead, the impurities are swept forward in the molten zone. Finally, all impurities reach the other end of the rod. This end is cut and discarded. The silicon and gallium used as semiconductors are also zone refined. Get this thing, it's very, very fun, doing metallurgy. I'm telling you. I know by the time you listen to my lecture, you will, pick interest to go for metallurgical engineering. Now, if you have not already started as a metallurgist, so that's why I am fighting so hard that Nigerians should get back on it, because it's really a nice field, to be an engineer and to work in the steel production to see how all of these things are being done. That's the future of our nation. Van Akel method, which is called the vapor phase refining. This method is based on the thermal decomposition of metal components. The process of decomposition of a compound into different substances due to the supply of a heat is called thermal decomposition. The titanium metal is purified by this method. When the impurity titanium metal is heated with an iodine at a temperature of 250 degrees centigrade, the volatile titanium tetraiodide is formed. The impurities left behind, as they do not react with iodine, now we have the impurities left because they are not reacting with iodine. The titanium tetraiodide vapor is passed over a hot tungsten filament at about 1,400 degrees centigrade, very hot. The vapor is decomposed and pure titanium is deposited on the filament and removed. The iodide is reused. You see the fun in metallurgy? So you have titanium reacting with iodine, and at 250 degrees centigrade, then you're going to get what we call the titanium tetraiodide. Titanium tetraiodide. Now this titanium tetraiodide is again under the tungsten filament, is heated again at 1,400 degrees centigrade, very high. Then you get a deposit of what? Tungsten filament of titanium. And then you have your iodine separate. Then you take your iodine and reuse it again. And it's fun. It's fun. Metallurgy is fun. So this concludes my lecture today. The lecture we have today deals with the process of extraction of metals from their ores and refining them. How do you extract the metals and how we refine them? So these are the things that I have just discussed in this lesson. So you will watch for the part 3 of steel making. So very soon. God bless. Thank you.